It is not, and never has been, an acceptable practice to install grounded receptacles in ungrounded systems by running a wire to a water pipe. The National Electrical Code, or NEC, has always required electrical systems to be properly grounded to ensure the safety of people and property. The NEC requires that all electrical systems be grounded and that the grounding system be capable of dissipating fault currents and maintaining a safe voltage potential. Proper grounding includes connecting the grounding electrode conductor, or GEC, to a metal underground water pipe, the metal frame of the building, or other approved grounding electrode. The GEC must be a minimum of #6 AWG copper or #4 AWG aluminum, as outlined in NEC 250.50. In the past, some older houses were wired with ungrounded systems which did not have a connection to a grounding electrode. This practice was never considered acceptable, and it is dangerous because it does not provide a path for fault currents to dissipate, which can lead to electrical fires or shocks. It is not safe or code compliant to simply install grounded receptacles on non-grounded systems. The addition of a grounding wire, such as #12THHN, to a water pipe does not create a proper grounding system. To correctly ground the non-grounded system, a qualified electrician must install a grounding electrode and connect the GEC to the electrical panel and all grounded outlets. Improper grounding can create a shock hazard for people using the electrical outlets. It can also lead to overcurrent conditions which can cause electrical fires. Non-grounded systems are not compatible with modern electrical devices that require a grounding connection. Adding grounded receptacles to non-grounded systems using a green #12THHN wire running to a water pipe is not an acceptable practice and poses a serious safety hazard. It is essential to have a qualified electrician upgrade the electrical system to meet current NEC grounding requirements to ensure the safety of your home and its occupants. Grounding is a critical aspect of electrical safety, designed to protect individuals from electric shock and to prevent electrical fires. An electrical system's grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly interrupt the circuit. In a properly grounded system, if a fault occurs, such as a live wire coming into contact with a metal enclosure, the fault current will flow through the grounding system back to the source, tripping the circuit breaker and disconnecting the power. This prevents the metal enclosure from becoming energized, which could pose a serious shock hazard to anyone who touches it. The grounding electrode conductor, or GEC, is the conductor that connects the electrical system's grounding point, typically at the service panel, to the grounding electrode. The grounding electrode is a conductive object that is buried in the earth and provides a connection to the earth. Common types of grounding electrodes include metal underground water pipes, ground rods, and ground plates. The size of the GEC is determined by the size of the service entrance conductors as specified in the NEC Table 250.66. The GEC must be properly sized to safely carry the maximum fault current that could occur in the system. The NEC also specifies the requirements for the installation of grounding electrodes. For example, ground rods must be at least 8 feet long and must be driven into the ground at least 8 feet apart. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, such as having at least 10 feet of direct contact with the earth. Non-grounded electrical systems, also known as ungrounded systems, do not have a direct connection to earth. While these systems were used in the past, they are no longer considered safe or code compliant for residential applications. In an ungrounded system, if a fault occurs, the fault current does not have a low impedance path to return to the source. This means that the fault current may not be high enough to trip the circuit breaker, and the metal enclosures of electrical equipment can become energized, posing a shock hazard. One common misconception is that simply connecting a wire from a receptacle's grounding terminal to a nearby water pipe will provide adequate grounding. This is not the case. Water pipes may not provide a reliable grounding path, and they may not be able to safely carry the fault current. Additionally, connecting to a water pipe may create a potential difference between the electrical system and the plumbing system, which could lead to corrosion or other problems. When upgrading an ungrounded electrical system, it is essential to install a proper grounding system that meets the requirements of the NEC. This typically involves installing a grounding electrode, connecting the GEC to the grounding electrode in the service panel, and ensuring that all metal enclosures and equipment are properly bonded to the grounding system. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. This includes bonding the metal enclosures of electrical equipment, metal conduit, and metal water pipes. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electric shock. The NEC specifies the requirements for bonding in Article 250. Bonding jumpers are used to connect different metal parts together. The size of the bonding jumpers is determined by the size of the circuit conductors, as specified in the NEC Table 250.102. It is important to use the correct size bonding jumpers to ensure that they can safely carry the fault current. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to protect against electric shock. GFCIs are designed to detect small imbalances in the current flowing through a circuit and to quickly interrupt the circuit if an imbalance is detected. GFCIs are typically installed in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires GFCIs to be installed in all new construction and in many existing installations. Arc fault circuit interrupters, or AFSIs, are another type of circuit breaker that can help to prevent electrical fires. AFSIs are designed to detect arc faults, which are dangerous electrical arcs that can occur when wires become loose or damaged. AFSIs quickly interrupt the circuit when an arc fault is detected, which can help to prevent electrical fires. The NEC requires AFSIs to be installed in many areas of the home, such as bedrooms, living rooms, and dining rooms. When working with electrical systems, it is important to always follow safe work practices. Always to energize the circuit before working on it, and use appropriate personal protective equipment, such as rubber gloves and safety glasses. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work. A qualified electrician will have the knowledge, skills, and experience to safely and correctly install and repair electrical systems. They will also be familiar with the NEC and other applicable codes and standards. In summary, grounding is a critical aspect of electrical safety, and it is essential to have a properly grounded electrical system to protect against electric shock and to prevent electrical fires. Do not attempt to create a grounding system by simply connecting a wire from a receptacle to a water pipe. Instead, hire a qualified electrician to install a proper grounding system that meets the requirements of the NEC. This will help to ensure the safety of your home and its occupants. The NEC, specifically Section 250.130c, provides guidance on replacing non-grounding type receptacles with grounding type receptacles. It outlines the conditions under which this is permitted, mainly involving extensions from existing branch circuits that do not have an equipment grounding conductor. Firstly, a grounding type receptacle can be installed where grounding means does not exist in the receptacle enclosure, but only if a ground fault circuit interrupter, or GFCI, protection is provided. Secondly, the grounding type receptacle must be marked GFCI protected and no equipment ground. This alerts users that the receptacle is protected by GFCI but does not have a direct equipment ground. Alternatively, a grounding type receptacle can be installed if it's connected to a grounding electrode conductor as described in NEC Section 250.130c. However, this method is generally not recommended and is only applicable under very specific circumstances. It is important to understand that simply connecting a wire from the grounding terminal of the receptacle to a nearby water pipe is not an acceptable or safe grounding method. This is because water pipes may not provide a reliable grounding path and can pose other risks. Proper grounding requires a connection to a grounding electrode system, such as a ground rod or connection to the building's metal frame, as described in NEC Article 250. The NEC also allows for the replacement of non-grounding type receptacles with other types of receptacles. Firstly, a non-grounding type receptacle can be replaced with another non-grounding type receptacle. Secondly, a non-grounding type receptacle can be replaced with a GFCI protected receptacle, as described above. Thirdly, an ungrounding type receptacle can be replaced with a grounding type receptacle if GFCI protection is provided and the receptacle is marked accordingly. When dealing with all the homes that have ungrounded electrical systems, it is often best to consult with a qualified electrician to evaluate the entire system and determine the best course of action. In many cases, upgrading the entire electrical system to include proper grounding is the safest and most reliable solution. In addition to the information provided in the NEC, there may be local codes and regulations that apply to electrical work. It is important to check with the local authorities to ensure that all work is performed in accordance with these requirements. The practice of running a #12 THHN wire to a nearby water pipe from a grounding receptacle in an ungrounded system might seem like a quick fix, but it's a dangerous and non-compliant solution for several reasons. Water pipes are not designed to serve as grounding electrodes, and their effectiveness as a grounding path can vary widely. Firstly, the electrical conductivity of water pipes can be affected by factors such as corrosion, mineral buildup, and the presence of non-conductive fittings or couplings. Secondly, water pipes may be disconnected or replaced with non-metallic pipes, which would eliminate the grounding path altogether. Thirdly, connecting an electrical ground to a water pipe can create a potential difference between the electrical system and the plumbing system, which can lead to corrosion of the pipes and other plumbing components. Even if the water pipe is made of metal and provides a continuous path to ground, it may not be able to handle the fault current that could occur in an electrical system. Fault currents can be very high, and if the grounding path is not adequate, it can lead to overheating, arcing, and potentially fire. The NEC specifies the requirements for grounding electrode systems in Article 250, and these requirements are designed to ensure that the grounding system is safe and effective. A proper grounding electrode system typically includes a combination of grounding electrodes such as ground rods, ground plates, and connections to the building's metal frame. The size of the grounding electrode conductor, which connects the grounding electrode system to the electrical panel, is determined by the size of the service entrance conductors as specified in NEC Table 250.66. When upgrading an ungrounded electrical system, it is important to consider the overall condition of the system and to address any other safety concerns. This may include replacing old or damaged wiring, upgrading the electrical panel, and installing GFCI protection in areas where it is required. It is also important to ensure that all electrical work is performed by a qualified electrician who is familiar with the NEC and local codes. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electric shock and fire. One of the most common misconceptions about grounding is that it is only necessary for safety. While safety is certainly the primary concern, grounding also plays an important role in the proper operation of electrical equipment. A properly grounded system helps to reduce electrical noise and interference, which can improve the performance of sensitive electronic devices. Grounding also helps to prevent voltage fluctuations, which can damage electrical equipment. In addition to the safety and performance benefits, grounding is also required by the NEC and other electrical codes. Failure to comply with these codes can result in fines, penalties, and even legal action. Therefore, it is important to ensure that all electrical systems are properly grounded and that all electrical work is performed in accordance with the applicable codes and standards. When evaluating an existing electrical system, it is important to look for signs of improper grounding. This may include loose or corroded connections, damaged wiring, and the absence of a grounding electrode system. If you suspect that an electrical system is not properly grounded, it is important to contact a qualified electrician to perform an inspection and make any necessary repairs. Do not attempt to repair or modify an electrical system unless you are qualified to do so. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electric shock and fire. The statement that adding grounded receptacles to non-grounded systems using a green #12 THHN wire running to a water pipe is not an acceptable practice and poses a serious safety hazard cannot be stressed enough. The goal is to make sure people understand the very real dangers involved. Relying on a water pipe for grounding is problematic because the electrical continuity of water pipes can be compromised by plastic fittings, corrosion, and other factors. In such cases, the grounding pattern may be ineffective, leaving individuals vulnerable to electric shock. Furthermore, connecting an electrical ground to a water pipe can lead to galvanic corrosion, which can damage the plumbing system and create potential health hazards. A proper grounding system should include a dedicated grounding electrode, such as a ground rod or a connection to the building's metal frame, that is specifically designed and installed for grounding purposes. The size and type of grounding electrode should be determined based on the size of the electrical service and the soil conditions at the site. The grounding electrode conductor, which connects the grounding electrode to the electrical panel, must also be properly sized and installed to ensure a low impedance path for fault currents. When upgrading an electrical system, it is important to address all aspects of the system, including the wiring, the electrical panel, and the grounding system. The wiring should be inspected for damage, deterioration, and improper connections. The electrical panel should be inspected for corrosion, loose connections, and proper labeling. The grounding system should be inspected for proper connections, adequate size, and compliance with the NEC. In addition to the technical aspects of grounding, it is also important to consider the human factors. People need to be educated about the importance of grounding and the dangers of improper grounding. They should also be taught how to recognize the signs of electrical problems and how to respond safely. One way to promote electrical safety is to install ground fault circuit interrupters, or GFCIs, in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. GFCIs are designed to detect small imbalances in the current flowing through a circuit and to quickly interrupt the circuit if an imbalance is detected. This can prevent serious injury or even death from electric shock. Another way to promote electrical safety is to install arc fault circuit interrupters, or FSIs, in areas where there is a high risk of electrical fires, such as bedrooms and living rooms. FSIs are designed to detect arc faults, which are dangerous electrical arcs that can occur when wires become loose or damaged. FSIs quickly interrupt the circuit when arc fault is detected, which can help to prevent electrical fires. When working with electrical systems, it is important to always follow safe work practices. This includes wearing appropriate personal protective equipment, such as rubber gloves and safety glasses, and using insulated tools. It is also important to de-energize the circuit before working on it and to test the circuit to make sure it is de-energized. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work. A qualified electrician will have the knowledge, skills, and experience to safely and correctly install and repair electrical systems. They will also be familiar with the NEC and other applicable codes and standards. Remember, electrical safety is everyone's responsibility. By understanding the principles of grounding and following safe work practices, we can all help to prevent electrical accidents and injuries. In conclusion, grounding is an essential safety feature of electrical systems that protects people from electric shock and prevents electrical fires. Improper grounding can create a serious safety hazard, and it is important to ensure that all electrical systems are properly grounded and that all electrical work is performed in accordance with the applicable codes and standards. The NEC provides detailed requirements for grounding electrical systems, and it is important to follow these requirements carefully to ensure a safe and effective grounding system. When in doubt, it is always best to consult with a qualified electrician to get the job done.